So good morning, everyone. I'm Khushbu Chitre. I'm a PhD scholar at IIIT Delhi. So today I'm going to present my work on titled "The Road Not Taken: Exploring Alias Analysis-Based Optimizations Missed by the Compiler," which is co-authored by my advisors, Dr. Piyush Kedia and Dr. Rahul Purandre. So this is the outline of my presentation. So first 13 slides talks about the limitations of existing static alias analysis implementations. The next 4 slides discuss some of the prior works that tries to address this limitation. Next 2 slides introduces our approach in brief, and next few slides describes our approach in detail, and the remaining slides presents our results and insights. So let's start with the presentation. So we have generally limited resources on any given systems. So programmers want to write efficient programs in such a way that they use the available resources in an optimal fashion. However, this task is difficult to achieve manually. Therefore, it must not be left to the programmers themselves. So compilers try to automate this process of transforming the program into its optimal version while maintaining the behavior of the program. And this process is known as code optimization. So these are some of the standard optimizations. However, our focus is on the 4 optimizations which are highlighted in bold here. Out of these 4 optimizations, loop vectorization is one of the most effective optimization, as it can theoretically speed up the performance of the program by 4x or more. So let's talk about loop vectorization in brief. So loop vectorization converts the scalar implementation of a loop to its vector implementations, which instead of performing same operation on a pair of operand, performs the same operation on multiple pair of operands in parallel. And such loops are said to be vectorized. However, a loop can only be vectorized when the memory locations corresponding to the operands never overlaps with each other. So clearly, the information related to the memory overlappings is very crucial to loop vectorizations as it might introduce some data inconsistencies. So this information can be obtained by performing alias analysis. So alias analysis determines whether a pair of pointers point to overlapping memory locations. This information is further used to compute memory dependencies within a program. Further, this information is used by many optimizations, including loop vectorization. So there are 2 ways in which alias analysis can be performed. First is intra-procedural alias analysis, which does not preserve the information across the function boundaries. So for example, when we consider this example, here when we call function fun, 3 pointers are passed as arguments to this function. As we can infer from the figure, that these 3 pointers never point to overlapping memory locations. However, intra-procedural alias analysis does not preserve this information. It follows a conservative approach and assumes that these pointers might point to overlapping memory locations. And further, this information is provided to the compiler. So there is another way of performing alias analysis, which overcomes the limitation of intra-procedural alias analysis. And this, it basically performs the alias analysis intra-procedurally, which preserves the information across the function boundaries. So for the same example, inter-procedural alias analysis can identify that these pointers, it basically preserves that information that these 3 pointers never point to overlapping memory locations. And this information is further provided to the compiler. However, preserving this information is itself a difficult task, as it is memory intensive and increases the compilation time as it involves the lot of computations. Therefore, inter-procedural alias analysis is precise but is not scalable for real-world applications, unlike intra-procedural alias analysis, which is scalable but imprecise. So to overcome, to maintain the scalability, most of the compiler developers choose to perform intra-procedural alias analysis over inter-procedural alias analysis. However, this reduced precision ultimately leads to missed optimization opportunities, resulting in less efficient program than expected. And this affects the performance of the program as well. So to deal with this imprecision, some of the prior works suggest one possible solution to improve the precision at the granularity of loops while maintaining the scalability. Generally, most of the time of a program is spent in the loop. Therefore, there are high chances of getting some benefits. So that is why these approaches focus on loops. So the solution combines loop versioning with dynamic checks. So such approaches creates two copies of the loop, where first copy is the original loop and the second copy is the annotated version of the loop, which involves the precise non-overlapping memory location information. Further, when this annotated version of the loop is fed to the compiler, compiler can enable potential optimization opportunities. So that is why we also refer to this version of the loop as optimized loop. Then after that, these approaches inserts dynamic checks before the both versions of the loop, just to verify that whether the annotations hold at runtime or not. If those annotations hold, then the optimized version of the loop is executed. Otherwise, the unoptimized version of the loop is executed. Several prior works are based on this idea. So these are some of the code snippets from spec benchmarks where the loop bounds are not loop invariants. So there are three approaches which actually tries to add range-based dynamic checks, which checks if the range of memory access inside the loop, whether they are overlapping or not. And based on the loop bounds. So such approaches requires the loop bounds to be known in advance. However, loop bounds can only be known in advance if they are loop invariants. Loop invariance is a property of a program which remains true before and after every iteration of the loop. So as for these code snippets, the loop bounds are not loop invariants. The prior three approaches which adds range-based dynamic checks, which are actually lightweight checks, they fails to work on these code snippets. So one of the prior works introduces a purely dynamic approach which can handle these cases. So that approach disambiguates the pointers based on the starting addresses of the objects. So however, when the memory allocation is done, the starting address is stored in the form of red-black tree, leading to big O of log n dynamic checks. Thus, this approach is not scalable for real-world applications. So our approach reduces the overhead of dynamic checks to constant time by using a segment-based custom allocator. So just to summarize, our approach reduces the overhead of dynamic checks and works on the loops where the bounds are not loop invariants. So our approach offers both scalability and loop coverage as compared to the purely dynamic approach. So let's take a look at our approach in detail. So these are the four main components of our approach, that is loop versioning, feedback from static optimizations, segment-based allocation, and dynamic checks. So let's start with the loop versioning. So as the name suggests, the purpose of this component is just to create two versions of the loop and annotates one of the version by inserting the required information. So at first it creates a copy of the loop, annotates it with the non-overlapping memory locations information that belongs to the body of the loop, and this modified version of the loop is known as annotated, we call it as annotated loop. So the output of loop versioning is two copies of the loop, annotated and original. Further, this annotated copy of the loop is fed to the loop-based static optimizations, and it basically provides two types of feedback. First, whether the loop has a potential to be optimized further based on the additional information. Second, the required dynamic checks for the optimizable loops. So it first checks if that loop has been transformed or optimized. If no, then the annotated version of the loop is simply discarded. Otherwise, we just compute the dynamic checks. So let's take a look at how we compute the dynamic checks. So the dynamic checks are computed based on the optimization potential of that loop. So it first checks if the loop is vectorizable. So as we discussed earlier, if the loop is vectorizable, then there should not be any memory overlappings in between the inside the body of the loops, like whatever memory locations are there. So we just add the dynamic checks between all the read-write and write-write pointer pairs. Now, if that loop is not vectorizable, then it is still possible that the loop can be optimized by removing some read or write memory access from the body of the loop. So if a read is removed, then we just need to ensure that that specific read is never updated inside the loop body. So we add the dynamic checks for between the read-write pointer pairs corresponding to the removed read. Then if a write is removed, then we need to ensure that that specific write is never read or updated inside the body of the loop. So we add the dynamic checks between the write and all the removed write and all the read-write pointer pairs. So before going into the, instrumenting the dynamic checks, let's take a look at how our custom allocator performs segment-based memory allocation. So our custom allocator constrains the allocation size and alignment of the memory allocation to the nearest 2 to the power k. So our segment-based allocator maintains a list of segments, and this figure shows the structure of one segment. Here, every segment is divided into fixed size slots. Different segments have slots of different sizes. Further, first 8 bytes of the segment stores its slot size. And the size and alignment of every segment is 4 GB. So for example, if we want to allocate memory of size, say 20, so the size and alignment of that object is set to 32, and the memory will be allocated from the segment where the initial 8 bytes stores size 32, which represents the slot size. So our dynamic checks are based on the object size. So our dynamic checks just computes the difference between the memory locations and compares it with the size. So whether that size, whether the difference is greater than or equal to the size or not. So if it is greater than equal to size, then the memory locations are not overlapping. So at first, here we just compute the starting, so given an internal address, we just compute the starting address of the segment by resetting the last 32 bits. And once we have the starting address of the segment, we just fetch the initial 8 bytes of that segment, which represents the slot size. And then we use that slot size and compare it with the difference of the given given pointer locations. So by performing an XOR operation. So to summarize our approach, this figure shows how all the components of our approach works together. At first, loop versioning creates two copies of the loop, which is the annotated and the original copy. Then this modified code is fed to the static optimizations for the feedback, which filters out those loops which cannot be optimized based on the additional information. And for the remaining loops, we just compute the dynamic checks, which are further instrumented. The transform code is fed to the compiler to convert it to the executable, which is linked to our segment-based allocator. The executable is run with the given inputs to get the performance benefits. So we implemented these four components in a tool, in a LLVM-based tool we named as Scout. So we additionally use a profiler to identify the loop which actually got benefited at runtime, and we just filters out those loops which shows some kind of performance degradation, which is possible when the overhead of dynamic checks overweighs the associated performance benefits. So coming to the evaluation, we evaluated our approach on the following two benchmark suits: Polybench, which represents the bunch of micro benchmarks, and Spec, which represents some real world benchmarks such as GCC and Perl bench compiler. The results indicate that the performance benefits of more than 3% can be achieved for 6 polybench benchmarks, which are shown in this graph. So this graph represents, the x-axis represents the benchmark name and y-axis represents the performance benefits. So the performance benefits are estimated by computing the percentage decrease in the execution time with respect to the native execution time of the benchmark. We observed a maximum performance benefit of around 51% for one of the polybench benchmark. So this graph indicates the performance benefits of spec benchmarks. We recommend using Scout with the 4 benchmarks shown in this graph. So for these 4 benchmarks, the performance benefits were more as compared to the overhead of our custom allocator, and for remaining benchmarks, it was not the case. So the overheads were more as compared to the benefits. So we observed a maximum performance benefit of 0.89% for one of the spec benchmarks. Further, we found several code patterns in spec benchmarks where the loop bounds are not loop invariants. This indicates that these are frequently occurring cases in real world applications. So many code snippets resulted in a performance benefit of more than 20%, with a maximum performance benefit of around 77%. So Scout enabled the following optimization opportunities, that is loop invariant code motion, global value numbering, dead store elimination, and loop vectorization. So our results further indicate that many loops can be potentially vectorized with the additional information provided, and these loops were not vectorizable earlier. So these are the memory overheads of our custom these are the overheads of our custom allocators. So memory overhead lies in between -2.29 to 34.89%, and the CPU overhead lies between the -2.57 to 8.36%. However, we observed that only 3 of 16 benchmarks resulted in a CPU overhead of more than 3%. In future, we would like to reduce these overheads. In conclusion, our approach can be scaled to real-world applications as the dynamic checks can be performed in constant time. It further covers the loop where the bounds are not invariants, and it enables many optimization opportunities which were missed earlier. Thank you. I'm happy to take questions now.
Hi. So this is kind of a left field question for you, but and I don't know if you're familiar with Rust, the programming language, but in that language, you can't, like, if you have references to arrays, you can't have one reference that writes to the array and another reference that writes to the same overlapping memory. So the problem kind of goes away completely.
So can you just repeat?
Yeah, that wasn't very well explained. So your whole problem, right, is that you have a reference to a range of two references to a range of memory that and the ranges overlap, right? And you write to one range and you read from the other range. No, that's it, right?
In this same array you're saying, right?
Yeah, the same memory overlapping memory locations. So some programming languages can prevent that can prevent you from having these overlapping ranges. Have you guys looked at that at all? Have you thought about how much of this is because in C or Fortran it's easy to have overlapping memory ranges?
Yeah, so in our case, this is like one limitation that if we are trying to access the memory locations in the same array, so they cannot be distinguished because of the fact that the base address will always remain the same in our case. So yeah, this is one limitation. But we saw that these cases were not much, at least in the spec benchmarks. So for now, right now we are not handling those cases.
So you said there were a few benchmarks where the costs of your approach outweigh the benefits. Did you see any common pattern in those situations?
A common pattern?
So something in common on the benchmarks where it was actually a net negative, your approach?
Yeah, so actually there were two reasons of our overheads are being like more, specifically the CPU overhead. One is that what we are doing is we are converting the stack allocations, or you can say we are just replacing the stack allocations with calls to malloc and free. So that is one thing. And apart from that, obviously this will ultimately affect the cache performance. So that is why the CPU overheads are high. And yeah, so these were the main reasons for, two reasons for the CPU overhead. And memory overhead is because of the fact that we are constraining the size and alignment, so specifically the size. So that is why. So these were the common reasons that we found out.
Do you have any ideas on how to deal with that to try to improve performance further?
Sorry.
Do you have any ideas on how to resolve those problems so you can make your approach even more effective?
Sorry, I'm not getting that.
So do you have any, in these two instances where it was a net negative, do you have any ideas on how you might overcome these challenges to make it even more effective?
Yeah, so one thing we are trying to do is, right now what we are doing is, we are kind of replacing or constraining the size for all set of memory allocations which are there. So one possible solution to this is just to kind of know in advance that these were the memory locations that we ultimately need to kind of add some dynamic checks in between and just constrain the size for those memory locations. So something like that we are trying to do in the next one.
Thank you for your talk. I'm not entirely sure how applicable your technique is to languages that are typically just-in-time compiled, but the general technique, do you think that would make sense in a runtime compilation system?
Yeah, I think because like right now we are handling some set of loops, but this is I think a general technique which can be further implemented for other languages as well by maybe modifying that allocator, because that is the one thing which which is the main kind of gist of this entire disambiguation part. So if we just modify it according to whatever languages we want to, or whatever constraints we have in those languages, then I think, yeah, it's more of a general approach that we can use.
Do we have any more questions? All right, let's thank our speaker.